All right, this week we studied the metallic bond. Now, if you have not watched that 7-minute video that I put last week into Canvas, I would strongly recommend you watching that. It's got better animations than I have, and I think it does a good job of explaining the difference between metal cations, the metallic bond versus the ionic bond. But I'm just going to review some of the key points and talk about a few of the things and go a little more depth than that video didn't quite do. All right, so the metallic bond, much like the ionic bond, a similarity in it is that we still do have the attraction between a positive particle and a negative particle. But in an ionic compound, that attraction is between a positive cation and a negative anion, because the metal atom donates its valence electrons to the nonmetal, making positive and negative ions. In a metal, however, the metal atom donates its valence electrons to the C. So the negative particles actually valence electrons that are free to move about throughout the material. And that's why they call it the electron C model, because the electrons kind of act like a C, almost a fluid that the metal cations are floating in. But again, we have the metal cations that are positive, and it's an electrical attraction between the positive metal cations and the C, the negative valence electrons that are floating around. And that is the metallic bond. Both the metallic bond and ionic bond look at Coulombic attraction, and therefore positive and negative particles attract to one another. So when you see a chunk of sodium metal, it is not a bunch of neutral atoms that are packed together, held together by things that we call intermolecular forces of attraction, which we'll study more with molecular compounds later in the year. So this would be a very weak attraction if they were neutral atoms, and therefore metals would not have very high melting points, which a lot of metals do have very high melting points. So a covalent bond or intermolecular forces would not explain why some metals have such strong bonding. And what we've found out through study is that the metal, if I have a chunk of sodium, it isn't neutral atoms. Instead, we have positive sodium ions, which have donated their electrons, so they're delocalized. Delocalized electrons means that the one that I just circled, this sodium cation, its valence electron might be way over here. Its electrons are free to migrate through the crystal or the chunk of metal. And it's delocalized, meaning it does not need to stay around this sodium atom. Okay, or say now a sodium cation. So that metallic bond is that attraction between the metal cations and the negative electrons. All right, now the strength of the metallic bond is given to us just like lattice energy. We're looking again at the same two variables. The first variable we'll look at is we look at the charge on the metal cation. Now there aren't anions, they're just metal cations. So we are looking at the charge of the metal cations, and with that, the metal cation that has a greater charge has donated more electrons. So the metal that has more valence electrons and donates more valence electrons to the C will have a more positive charge. And the more positive charge the cation, the more electrons donated to the C, there will be a stronger metallic bond because there are more electrons for the cations to be attracted to. Okay? So the more electrons that are donated to the C, the more valence electrons it has, typically it has a stronger metallic bond. The second variable to look at is if both of the elements donate the same number of electrons and form the same metal cation charge, then again we look at size. And again, just like ionic, the smaller it is, the stronger it is. When we go down families, when we go top down the periodic table, the metal cations are getting larger and larger, and we expect then with this phenomenon that when we go down a family on the periodic table, a family that is a family of all metals, we expect that the melting points will decrease. And they'll decrease because the metals donate the same number of electrons because they're in the same family, but the metals that are further down the family are bigger, and therefore there's not as much electrons to surround that bigger surface area of the cation, and the melting points decrease. So metals further down a family will have weaker metallic bonds and therefore will have lower melting points. Again, melting point is the measurement that we can use in lab that can dictate or tell us how strong the bond is. All right, so pause the lecture real quickly and identify, based on the positions of these elements on the periodic table, who you expect to have the strongest, weakest bond to the strongest bond. So please do that now. All right, if you did it correctly, the metal that would have the lowest melting point in this set would be rubidium, because it is only donates one electron. It's in group 1, so it forms a +1 charge. It is one valence electron, just like sodium. But sodium is higher up in the family, so it has smaller metal cations, and therefore the electrons will be able to fill around the surface area much easier. So the smaller the metal, the stronger the metallic bond. And then magnesium donates 2 electrons and aluminum donates 3. So all the metal cations would be +3 for aluminum, and each aluminum has got 3 electrons in C, creating a lot of electrons floating around for a lot of electrical attraction. Okay? So that's how we determine metal strength. Look at the number of valence electrons it'll donate, and then look at size, much like ionic compounds. All right, some other properties of metals. Metals are malleable and ductile. I've drawn here a crystal lattice of an ionic compound. Ionic compounds are brittle, but metals are malleable. Why? An ionic compound has a very strong bond of alternating positive and negative cations and anions. But if I take a hammer and I apply a force to it and cause it to shift down just one ion by applying a force to a crystal, we end up having positive and positive, negative and negative that get close to each other. And they repel, and that causes the metal to just separate apart, okay? To be brittle and just to smash apart, okay? To cleave from itself. But in a metal, if I look up here, in a metal, it isn't a strict, rigid configuration. The electrons are free to move about, and they're acting like a sea. And if you take a hammer and hit into a pool of water, the water molecules just flow around the end of the hammer. Same thing here. If I take and I apply a force to it and I shift all these metal cations down, the electrons still move with the cations and just stay in between the cations themselves because of their free mobility, acting almost like a fluid. And it just wraps around the material and can bend. So because the metal ions in a metal, the electrons are free to move about, unlike in ionic compounds where they're not, they're very rigid, that mobility of those valence electrons acting like a sea stay in between the cations, preventing repulsion from occurring. Metals are conductive in any state. If I were to hook a wire and send electrical current into a metal, an electron comes in, and then an electron on the other end can kick out because they're free, they're delocalized. They are not set to a specific ion. So electrons can flow in and kick out because, again, the electrons have mobility. Unlike in the ionic compound, the anions do not have freedom to move. Metals are not soluble in water or other solvents. They tend to be very insoluble materials. Okay? Metals, they have a much wider range of melting points. Some melt around room temperature, maybe a little above, and some don't melt for several thousands of degrees like titanium. So they have a wide range of melting points, much more wide range than ionic compounds. And again, what separates that is the strength of the bond. Metals that donate more electrons and are smaller, they will have very large melting points. Metals that are larger and donate only one will have melting points that are much closer to room temperature and tend to have low melting points on average. Okay? An example is titanium. Titanium is one of the elements that tends to have one of the largest melting points of metals. It donates 4 electrons to the C per particle, and it's one of the smallest metal ions, and therefore it has a very strong bond and therefore has a high melting point. Hardness is very similar to the melting boiling points. The more electrons it donates, and the smaller it is, it's going to be a harder metal. Okay? This is why elements in the S block, these are the most reactive metals because they tend to be large, they have low coulombic attractions, but S block metals tend to be very soft because they only donate 1 or 2 electrons, and they tend to be larger ions compared to how many electrons they donate, and therefore they tend to be quite soft. So the elements that tend to have lower melting points tend to also be softer metals as well. Okay? One last concept of metals is alloys. An alloy is a mixture of metals. Now, sometimes an alloy can be just one metal and other nonmetals mixed in. For an example, carbon-based steel, where carbon is a nonmetal and we have iron, which is the metal. So an alloy does not have to be all metals. It can have some nonmetals mixed in, but an alloy is defined as a mixture of a material in which one of the substances is a metal. Okay? So there are 2 basic types of alloys, substitutional and interstitial. Okay? Here we see 14 karat gold, in which these greenish color materials is a gold cation, and the silver ones are silver. This is called a substitutional alloy. Interstitial, we can see the red particles as being the iron cations, and then the black atoms are carbon. Interstitial. All right, so real quickly, look at those 2 pictures. What do you think is the main difference between these 2 alloys? In a substitutional alloy, the metal cations tend to be of similar size. Now, why would I want to infuse another metal into another metal in the alloy? Well, oftentimes the metal that we substitute into it tends to be able to donate more electrons to the C. And if you infuse a metal that donates more electrons to the metal that there already is, since more electrons are being donated into the C, that's going to make the bond stronger. That's going to increase the hardness of the material and increase the melting point. It's going to increase its durability. So that's often why we end up doing that, is by mixing different metals together, is to increase the number of electrons in the electron C model and increase the material hardness and metallic bond and melting point. Interstitial, you'll notice that the substances are of different sizes. And therefore, carbon doesn't donate any electrons to the C, but the carbon atoms fit in between the other metal atoms, keeping them the same distance away, but packing in between. And that packing in between those cations, that increases the strength of the material because there's not much space between the particles. And something like carbon that's very lightweight, it tends to increase the strength of the material with not adding a lot of extra mass. And therefore, it really makes the material much, much harder and stronger because it can pack in between the cations, improving its strength. Okay? And that is what I kind of just explained here with carbon and iron. Okay? Those carbon atoms are able to get in between. Just like if you took a glass jar and filled with marbles and then put pebbles of sand inside of it, there's a lot of space between those marbles. And filling in those gaps will improve the strength of the material. Okay? Sterling silver, as I said before, okay, copper has the ability to donate 2 electrons per particle, while silver only donates 1. So by donating more electrons to the C, more electrons will increase the strength or the metallic bond. That'll make the material harder. It'll make the material more durable, increase its melting point. And normal silver tends to be a little bit softer. And if you have totally silver materials and you try to use like a silver spoon that's perfectly made of silver, you put something that's very hot, that heat from, let's say, a soup or a tea would actually make the material be so soft that the spoon would no longer hold its form. So by adding that copper, it really improves the strength of the material and allows you to have something like sterling silver, which is used in a lot of fine dining ware sets. Okay. All right, so that's a metallic bond. So the key difference is the ionic bond is very rigid and strong, but the particles, the cations, ions, cannot move and migrate through it, versus in the metallic bond, the delocalized electrons are free to move about, and that those freedom of the particles to move about cause it to be very malleable and ductile, because it can mold and bend with the electrons always staying in between. And also it causes the material to be very conductive, because those free electrons allow current to flow through them very easily. All right, so these are the key properties. Later in the week, we're going to have a quiz, which will cover concepts of metallic and ionic compounds. It'll be the only quiz we'll have in this unit when it comes off of ionic and metallic bond properties. But that'll be later in the week. I'll open that up for you guys so you'll be able to take it. If you have any questions, again, don't be afraid to contact me.